Hello, my name is Ronnie Fexo, and this semester I worked on polyp segmentation and colonoscopy images. So colonoscopies are performed by doctors to prevent colon cancer. And in particular, they look for these growths called polyps, which as you can see here, uh, are precursors to colon cancer. So they want to remove these. But when they take these colonoscopy videos, thousands of frames are collected. So it's important to improve the automatic detection of these polyps so we have more efficient and reliable colonoscopy analysis. So I used a dataset called Cavazzier segmentation, which consists of 1,000 expertly annotated colonoscopy images in their polyp segmentation masks, as you saw on the last slideshow. And so what I did was test two UNets for medical image segmentation and PyTorch. I tested UNet++ and LinkNet, and I assessed them using DieSloss and visual inspection. And so I found that UNet++ performed better as a baseline. So I went ahead and focused on that. And as you can see here, a regular UNet is shown just by the black arrows and neurons, but the UNet++ has these additional dense skip nested pathways, which reduce the semantic gap between the feature maps and the encoder and decoder. And these connections are shown in the green and blue and red. And so then I did some experiments to find the optimal encoder backbone. And then once I found that, I did hyperparameter tuning. And then I embedded this uh, tuned model into a Streamlit app. And my initial takeaways from the experiments, at least, were that the backbone encoder was not extremely impactful. So I opted for the smallest backbone in terms of parameters because I had memory restrictions due to Google Colab. And so that was MobileNet version 2, which had about 20 times less parameters than all the other backbones I tried, like ResNet 34. And then I also found that the encoder depth was extremely important. And so the encoder depth set to 5 vastly outperformed encoder depths of 3 and 4. So now I'll show some examples. So if you go to this web app yourself, you can see that most of the results are pretty good. So I'll show one good example. So as you can see, the mask is very detailed and precise, and um, nothing to really complain about here. But I think it's more important or interesting to learn from the bad examples. That's where we can improve our model. So as you can see here, the location of the mask is pretty accurate, but the shape and size is terrible. And my guess for this, or my theory for this result, is because there's very poor illumination in the original image, and the boundaries of the polyps are not very well defined. Um, then another poor results here. So once again, the location is decent, but the shape of the mask is terrible. So you can see it detected this edge right here. But the interesting thing about this image is that it's very low resolution. And so it seems like the network can't really deal with that very well. And now I'll show some examples which aren't terribly predicted, um, but they do have some interesting results. So far we've seen that most of the time there's one polyp in the image, but this shows that the network can actually detect multiple polyps in the image, which is very important for patients who have high number of polyps in their colon. So it's important that the network is able to handle this scenario, which it can in this case. Then one more image before I wrap up. So it looks like there are 3 polyps here, but it only detects the ones in the middle and the right. And I think this is because these two have very strong round edges, which the network picks up. But over here on the left, the polyp is not as clear, even to the human eye. So it completely misses that. And this may be something to focus on in future iterations. So those are my findings, and thank you for listening.